so now we're going to look at the second main type of application for vectors, which is force. So it is common for more than one force to act on an object. And when that happens, we call the net force experienced by the object to be a single force vector called the resultant force vector. It's the sum of all the force vectors that are acting on the object. And this is very similar to what we were looking at with velocity. When you look at the velocity vector, the velocity with respect to the ground, with respect to the fixed stationary point, is the result of all the velocity vectors that are acting on it, on the object or the boat or whatever. And it's the same for force, right? So when we have all the forces acting on an object together, they create the resultant force vector, which is the force acting on the object all together. Okay, there is a special case where there is no motion at all that results from all the forces. And then when that happens, we say that the forces are in equilibrium. Equilibrium would mean that the sum of the force vectors is equal to zero, the zero vector. Zero itself wouldn't make any sense, but it has to be the zero vector. In other words, all the x components, the y components, the z components, they all balance out, right? So the component forces balance out, if you will, or cancel each other out. And we use that a lot to solve problems for things like this. Okay, so let's look at this one. There are two ropes attached to a sled, each being pulled by a different person. Kim pulls in a direction of 5 degrees west of due north with a force of 35 pounds. Kate is pulling in a direction of 12 degrees east of due north with a force of 20 pounds. Find the resultant force vector and the magnitude and direction of the resultant force. Now I know this seems like a really simple example, like, you know, who are Kim and Kate and why do we care? And the answer is we don't. You can imagine these could be tow trucks, or these could be, you know, airplanes towing something, or, you know, all sorts of things. So it's just a basic idea that you're looking at. Okay? But if it makes you happy to think of people pulling a sled, so be it. Okay. So everything we're caring about is really in the north and the east. So we're just going to graph that piece of it. We don't need the south in this particular case. All right, now the force vector for Kim. Kim is pulling 5 degrees west of due north. So not very steep, but there. They're pulling that way with a force of 35 pounds. All right, so that's the force vector for Kim. And then we have Kate pulling 12 degrees east of due north with a resultant force vector of, let's see here, with a resultant force of 20 pounds. So 20 pounds, so not as long and a little bit steeper. So this is 20, and this will be the force vector due to Kate. And let's think about the angles here for a second. So we know that the angle here is 5 degrees. And we know that the angle here is 12 degrees. I've not drawn these to scale, but that's okay. Okay, so we need to find the resultant force vector and the magnitude and direction of the resultant force. So there's some pull that's happening on this sled, right? Who's going to win out? Whose side is it going to end up on? We're going to find out. Okay, so the resultant force vector. Well, actually, let's deal with each one individually first. All right, so let's look at Kim's force. Kim has pulling with a force of 35 pounds. Now the angle we have to think about for a second. You can't just put 5 degrees in, because 5 degrees is not from the standard position, right? So we have to deal with it from the positive axis. That's how we work with angles. And so when I put 5 degrees in, that won't work because no software, no computer program in the world knows what I'm talking about. So we have to change that angle to the full angle, which would be 95, right? Starting over here and working your way all the way over would be 95. So 95 degrees. Okay, we can come up with a decimal approximation of that in a second. We'll find the other one first, and then we'll go make a computer do all of it. All right, so now let's find the force vector for Kate. Well, that's 20. So 20 cosine of an angle, 20 sine of an angle. Now, you can't just put 12 in. So 12 is this angle between the positive y-axis and Kate's vector, which that's no good to us because that's, again, not from the positive x-axis. That's how we measure angles. So we need to have the angle here. But remember, these two angles have to add up to 90 degrees. They're complementary. So that means that this is 78 degrees. So that will be the vector, or excuse me, the angle that we use in here for calculating this vector. And then we need an approximation. Okay, so we'll go grab Desmos because it's easy. Again, switch to degrees. I've shut this down since then, and it always switches back to radians. So you have to go change it to degrees to make it work. All right, so I need 35 cosine of 95. I need 35 sine of 95. I need 20 cosine of 78. And I need 20 sine of 78. And there we have them. We've got all the numbers. So I'm just going to write all those down. Okay, so they're written. So now the resultant force. The resultant force is the sum of the component forces. So it'll be Kim's force and Kate's force put together. Okay, so that would be negative 3.05 comma 34.87 plus, oh, one second, let me make that pink. There we go. Now I've color coded it. So it's the pink vector plus the blue vector, right? So it's Kim plus Kate right there. All right, so now we're going to add those up. So this would be 1.11. I just did that in my head. 4.16 take away 3.15. And then we'd add these two together, which would be 54.43. If I'm not mistaken. I'm pretty sure. I mean, I can double check it with Desmos, but I'm pretty sure. Okay, so that's that vector. So we wanted that force vector, and we have it. There's the resultant force vector. Done, right? Now we have to find the magnitude and direction of the resultant force. Okay, magnitude will be the size of the force vector, the length of the force vector. And we find that with the square root of 1.11 squared plus 54.43 squared. And then we will go find what that is. All right, square root of 1.11 squared plus 54.43 squared. And just out of curiosity, let's see if I was right. So, yep, 54.43, and I can leave that there. But the other one was 1.11. So there you go. So I'm rounding a bit, but that's okay. Oop, I already lost the answer. It's 54.44. And that, in this case, would be pounds, because they mentioned pounds as the unit. So it'd be 54.44 pounds. All right, now we just have to find the angle. Okay, because that'll get us our direction, right? Well, we remember that the tangent of theta is equal to the force components, so F2 divided by F1. So that would be from my resultant vector. So that would be 54.43 divided by 1.11. Therefore, theta, related, is the arctangent. It might not be theta itself. It's definitely a related angle. Is the arctangent of 54.43 over 1.11. And then we have to see where we end up. Although I think we're going to end up in quadrant 1, which will be fine. Right, quadrant 1 makes sense. So arctan of 54.44 divided by 1.11 gets us 88.8 degrees. And that's perfectly reasonable in this situation, to imagine that the resultant vector is going has a length of 54.44 and is ending up at 88.8 degrees. Right? So what's happening is the sled is here. This person's pulling pretty hard that way. This person's pulling less hard, but pulling at a steeper angle. And together they're resulting in something that's going like this, right? With an angle of 88.88 degrees. So pretty close to true north, but not quite. Okay, so 88.88 degrees north. Let me put it this way. The direction of that force vector would be 88.8 degrees north of due east. Or if you like, you could say it's 1.2 degrees east of due north. Right? It's pretty close to being pulled directly north. Okay, let's do the first one on the next page before we finish this video, because this one's not too terrible. In a three-way tug of war, one person exerts a force F1 of 8I minus 3J plus K, while a second person exerts a force of negative 2I plus 2K. What force must be exerted by the third person in order for the object at the center to remain motionless? Okay. So to remain motionless means we've hit equilibrium. We've achieved equilibrium. And what is the magnitude of that force? Okay, so if we have equilibrium, what that means is that force 1 plus force 2 plus the force 3 has to be equal to the 0 vector. Okay, so that would mean that force 3, which is the one we're looking for, would be equal to negative, we would subtract these two forces to the other side, negative force 1 minus force 2. That way we would achieve equilibrium. If this person can balance out these other two, if they're pulling in their particular directions and this person can counter the x, the y, and the z component, then we've got it. All right, well, we can find that, right? The negative of F1 would be negative 8I plus 3J minus K. And then we want to subtract, or if you will add, negative 2I. So let me do it this way. Minus a minus 2I. We want to subtract F2. So subtracting the negative 2 would mean plus 2I. There's no J, so plus 0J, if you will. And then minus 2K. Right? So if you want to look at it this way, this is the negative of F1, and this is the negative of F2. And then we're adding them together. Okay, so let's combine like terms. The i's go together. So I and I, so that becomes negative 6I. The j's go together, plus 3j, and the k's go together, minus 3k. There we have it. That would be how the third person has to tug in order to achieve equilibrium. The magnitude of that, let me write magnitude over here, would be the magnitude of F3, which is the length and or size of F3, which is the square root of negative 6 quantity squared plus 3 squared plus negative 3 quantity squared. Or if you like, you can just turn them all positive in your mind, right? So that is 36 plus 9 plus 9. So 36 plus 9 makes 54, or 55, sorry, 36 plus 5. 55, 64. So this is the square root of 64. Wait, no, it's not. I'm doing that, adding wrong. 36 plus 9 makes 45. There we go. 45 plus 9 makes 54. There we go. Now we're getting there. Sorry, I felt like I was going crazy there for a second. And then, of course, if we want a decimal approximation, we can get that. It would be the square root of 36 plus 9 plus 9. See, 54. So, well, here, I can copy and paste it. There we go, 54. So then the square root would be 7.35, and that would be newtons or pounds, depending on whether we knew this particular problem was in metric or in SI. It wasn't given to us, so it would be square root of 54 pounds or newtons, depending on if we have SI measurements or if we have metric measurements, whichever one, or 7.35 pounds or newtons. Again, they didn't give us the units, so we don't know which one we're working with here. Wait, it's not SI. SI is metric. I'm sorry. See, this is why I'm not a science teacher. This is SI. Metric is SI. It's like the system of units or the international system or something like that. This is imperial. It's the American system. Nobody else really uses it anymore, but except for engineers in the U.S. a lot. So this is the imperial system, the British system, the American system. Sorry. SI is metric. That's my fault.